Okay, are there any questions on the homework problems?
I had a question on homework chapter 2, 6C and 6B.
Okay, chapter 2, 6 what?
6E and 6D.
6E and 6D. Okay, let me take a look.
Can you go ahead and do 6C? That's the only one I couldn't do.
Okay, sure. Yeah. I think it's probably going to be easier for me to bring my laptop out here and open, but I can get to it. Hold on a second. Oh my gosh. Okay. Okay, is this the one that says an attacker at the base of a castle wall throws a rock straight up with the speed of 8 meters per second from a height of 1.4 meters above the ground? That's it, right? Yes? Okay.
Yeah, something like that.
Okay. All right. So let's see, 3.8 meters high. Okay. I'm going to draw the picture real quick, then I'll get where you can see me. Okay. So here's... Now your numbers might be a little different, but... And this is...
We can't see anything.
I know. I'm just drawing the picture. When I come back to the screen, I'll... Okay. So here's the rock. 8 meters per second. Okay. Okay. All right, so this is it, right? 3.8. I mean, your numbers may be a little bit different, but
Yeah, that's pretty much it.
yeah. Okay, so I think the first part says, will the rock reach the top of the castle, right? So did you have any trouble with that?
Um, I used the distance formula for that, but
Okay. Yeah. I mean, you know the initial velocity. Let's write down what we know. V initial is equal to, this is part A. V initial is 8 meters per second, or you should have a number close to that. Y initial is equal to 1.4 meters. Y final is equal to 3.8 meters. Okay. Or you could do Y final. Let's see. That's fine. All right. Y final is equal to, well, let's do it this way. If you make V initial and this set V final equal to 0, that's going to give you the maximum height, right? So you can, this is part A. So you can say, you can use V final squared minus V initial squared is equal to 2 or minus 2G Y final minus Y initial. And you can see, okay, well, is it going to reach 3.8 meters from that? Because you know V final 0, V initial 8 meters per second, Y initial 1.4, this is 9.8. So that's certainly one way you can do it. What was part B? Did anybody have trouble? If so, what is its speed at the top? Okay, fine. You can use that equation as well, huh? Find the change in. Let's look at C.
Yeah, that's the one I had trouble with. I try to use
Find the change in speed of a rock thrown straight down from the top of the wall at an initial speed of 8 meters per second and moving between the same 2 points. Okay, so for that case, for C, you have the object starting here, and this is 8 meters per second, okay? And it's ending here, right? It's going to end right there. So V initial is equal to, huh?
8 meters per second, right?
Yeah, this is meters per second. My number is 8 meters per second. So yours may be 7.9 or something. Is that what you're asking?
Oh, no, I was just, yeah, I think I was just given 8 meters per second as well.
Oh, okay. So V initial is negative 8 meters per second. V final is what we're looking for. Y initial is equal to 3.8 meters. Y final is equal to 1.4 meters. Okay. Solve for V final. So you get V final squared minus V, well, this would be minus 8 meters per second squared is equal to minus 9.8 meters per second squared times Y final minus Y initial. So this is 1.4 meters minus 3.8 meters. Okay. So you're going to get an answer for V final. Can somebody calculate this? Let's see. I'll calculate it. So get 2. And then let's change 64 plus, take the square root. I got 10.54 meters per second. That's going to be negative, by the way. Did anybody get that answer or something close to that?
The numbers on mine were a little bit different, but I got negative 10.07.
Yeah, okay. So the difference is V final minus V initial. So you get 2.54. So delta V is equal to negative 2.54. Really, for deltas, you don't typically, well, let's put the negative. I don't know if they're going to want the negative or not, but yeah, okay. Negative 2.54. Does that answer your question? Let's see. Negative 2.4. Okay, 2.54. Yeah. Okay, they don't want the negative. Deltas really shouldn't be negative, but, well, the way we're defining them, if it were a vector, well, they're saying speed, so it's not a vector, I think. 2.54, see, it looks like it's correct. Okay. Part D, does the change in speed of the downward moving rock agree with the magnitude of the speed change of the rock moving upward? Okay, well, you can check that. I mean, it's moving upward. You've got the rock slowing down that has the same acceleration between the 2 points, except it's slowing. Moving downward, it's speeding up. So you realize you have unlimited attempts on these. Not unlimited. I think it's like 100 or something attempts. But part E, there shouldn't be any, I'm not requiring an answer for part E. Let's see. If you look up here on points, if you look up there on the left where it says 2 out of 10 points or whatever it is, okay, let's see. That should be, ooh, how did that happen? That should be set to 0 for part E.
So could we just type n/a and then submit the answer and it'll give us the points?
Yeah,
Okay, cool.
yeah. I'll fix that, but that should be, like, part E should be set to 0. I don't know what happened with that. Something must have happened when because I had all of those set to 0. Oh my gosh. Okay, I'll fix that. I'm really glad you pointed that out. Let's see, on part. So yeah, you don't have to worry about any of the explanation parts. I'll fix that. So on 6, it's just A, B, C, D. Stupid software. Okay. Okay, any other questions on the homework problems?
I was a little confused on 5C.
5C, okay. All right, so for number 5, at t equals 0, one toy car is set rolling on a straight track with initial position. So this is very similar to what I did with the car and the truck. Negative 4.2 centimeters per second, then and a constant acceleration of 2.9 centimeters per second squared. At the same moment, another toy car is set rolling on an adjacent track with initial position 9.5 centimeters initial velocity, 5.2 centimeters per second, and constant 0 acceleration. Okay. At what time, if any, do the two cars have equal speeds? Okay, you got that. What are their speeds at that time? Okay. At what time, if any, do the cars pass each other? Well, it's a possibility that they may not pass each other, but we'll see, okay? So let me... All right. So there's one car, and it starts out at, what does it start out at? 17 centimeters. Oh, it's down here. And negative 4.2. Equal to, I'm drawing all this, I'll be with you in a second. So 9.5 centimeters and 5.2 centimeters per second. Okay. All right, oops. All right, this is what I got. So I'm calling this 1 and this is 2. So this one's down here at 17 centimeters and it's traveling in this direction and slowing down. This one is traveling at a constant velocity in this direction. And it started out, for me, started out at 9.5 centimeters. Okay? The question is, when, or I guess they're asking, yeah, when does x1 final equal x2 final? So This is almost exactly like the one I did with the car and the truck. The initial conditions are a little bit different, but nevertheless. Okay, so we need to write an equation for x1 final and x2 final and set them equal to one another and solve. So x1 final is equal to x1 initial. I'm going to keep it in centimeters. 17 centimeters plus, no, it's going to be negative. So it's going to be minus 4.2 centimeters per second times t plus 2.9 centimeters per second squared all over 2 t squared. So that's x1 final. That's the initial position for x1. That's the initial velocity. You have to keep the negative. That is the acceleration. For car 2, that's pretty darn simple. x2 final is equal to 9.5 centimeters plus 5.2 centimeters per second t. No acceleration. That's just that velocity times time. That's your initial position. There's the velocity. There's time. Okay. Set these, I'm going to erase this. Yeah. Set these equal to one another and see what kind of solution you get. So I'll put this on the left. I'm just setting them equal. Which way did I have it? Okay, x1 goes on the left. 17 centimeters minus 4.2 centimeters per second t plus 2.9 centimeters per second squared over 2 t squared is equal to 9.5 centimeters plus 5.2 centimeters per second t. Okay. Collect terms and solve. So I'll move this stuff over here. So you get 6.5, I guess. You get 6.5 centimeters. This is negative 4.2 minus 5.2, so that's 9.4 t, and this stays plus 2.9 over 2 is 1.45 centimeters per second squared t squared, and all of that is equal to 0. Okay. No, this is 7.5. 7.5. Put that into your calculator and solve. What do you get?
It's pretty much the quadratic formula.
It is the quadratic formula. You're right. Well, it's a second order polynomial equation, so solve it with your calculator or quadratic formula, however you want to do it. Can somebody give me the answers for this? T is equal to, should be 2 answers. Somebody's got their calculator going. I can do it, but it'd take a minute. What do you get? Anybody got an answer? Are you trying or?
Yeah, I'm putting it in the calculator.
Okay. All right. And the answer is, whoa, it's taking a while.
For the first one, I got 0.932.
0.932 seconds. What's the second answer?
5.55 seconds.
Okay, 5.55 seconds. That sounds reasonable. So that should work. That's the same situation where that first car went this way, is slowing down, then they passed fairly quickly, and then it started speeding up and caught it again 5.55 seconds later. That's the idea.
Where do you want us to turn our labs in? Do you want us to just cam scan like a PDF and then send it to you?
Yep, that's fine.
Okay.
But as long as I can read it and you email it to me, yeah, it's fine. No problem. Any other questions on the homework? Okay. If you haven't done the home or attempted the homework, I highly recommend it. Last time, we had some new ideas, just extending these ideas of displacement, velocity, acceleration to more than one dimension, namely 2 dimensions. And we had the position vector, which was just r, and it equals x I hat plus y j hat. Okay. So that's the position vector. It's just where you are in the plane, and it's a vector that points from the origin to your position in the plane. Displacement was an extension of this one-dimensional idea. Displacement is delta r, and it is r final minus r initial, so it's the difference in the two positions, your final minus initial. And if you write this out, this is x final minus x initial times I hat plus y final minus y initial j hat. And these little I hats and j hats keep with the directions. I hat points in the positive x direction, j hat points in the positive y direction. You can immediately develop velocity from this in 2 dimensions. Velocity is v as a vector, and this would be the average velocity. This is equal to delta r divided by delta t, and that's, well, that's this. I'm not going to write all that out. That's just this vector divided by the time. Okay, you can also write something for the velocity. If I just write this, this means the instantaneous velocity. This is equal to what? dr dt. Okay, and that's equal to d dx dt I hat plus dy dt j hat. Okay. This is what we had in 1 dimension. We're just adding on the y direction now. Okay. Acceleration. Acceleration is, let me rewrite this in one other way. Notation, notation, notation. This is v x I hat plus v y j hat. I mean, just to say that this is your velocity in the x direction, this is the velocity in the y direction. Okay? As far as acceleration goes, it's the same idea. Acceleration is equal to dv dt, and that's equal to I'm just going to write it as ax I hat plus ay j hat. It's just the acceleration component in the x direction, the acceleration component in the y direction. Okay. Any questions on that? It's all notation. I'm going to do an example with that now. Okay. You take a train trip. Maybe you go down to downtown Memphis and you get on the train down to New Orleans. Let's say that you go, well, we're not going to New Orleans, but let's say that we go 80 kilometers, slow train, 80 kilometers per hour for 3 hours east. So this is the east direction. Okay? The train takes a little turn. We're not going to worry about the radius here. And the train speeds up a little bit, goes 100 kilometers per hour at 30 degrees south of east. Okay? And it travels that speed. My vectors aren't going to be exactly right. Travels that speed for 2 hours. Okay. Well, this one should be shorter, really. Let's see, that's 240 kilometers. That's 200 kilometers. Okay, maybe about here. Okay. Question. What's R? What's delta R? Okay. Well, start out here, you can make this 0, 0. This is the starting position. Why not? Hold on a second. Doesn't have to be, but you certainly can make it 0, 0. Now there's all kinds of clever ways to figure out R final. I would just say figure out, I mean, this is easy as far as, you know, figuring out this distance, you find the components, and you can figure out this final position. So this is going to be our initial. This point is R, not R. Well, I'll make it the vector. This is R final. Okay. I don't like that. Okay. This is X final, Y final. All right. You're starting out up here. This is our initial 0, 0, but X initial, Y initial. Okay. So I want to find delta R. Then I want to find then I want to find V, the average velocity. Okay. I also want to find out what the speed is. So what's delta R? How can we do that? Well, if you can find out what these 2 points are, you can calculate delta R, right? Yeah. This is 3 hours east at 80 kilometers per hour. So this distance for this little part of the trip is equal to 240 kilometers. Right? That's for this first part. This distance, I'll put it in purple. This distance is 200 kilometers. 2 hours at 100 kilometers per hour. Okay? Well, delta R, we can figure out now. The X position here, you got 240 kilometers plus some distance in X. You can figure out X final from that. So X final, there are more ways to do this. I'm doing it this way, but X final is equal to, well, I went 240 kilometers in that direction. That was east. Now, 200 kilometers, 30 degrees south of east. So I want this little bit of distance to figure out what X is, X final. So that's plus 200 kilometers cosine 30 degrees, right? Are you guys still there? I just heard a bunch of click, click, click. Hello?
There.
Still there. Okay, good. You with me now? This is 200 kilometers. That's this distance. Cosine 30 degrees. That gives you X final. We'll calculate that in a second. Okay? Now for Y final, well, there was no change in Y along that first part of the trip, but in this part of the trip, okay, you went south And that is 200 kilometers sine 30 degrees with a negative in front. Yeah? You are below the x-axis here, and this side is 200 sine of 30. That one's easy. That's 100 kilometers. That's negative 100. Right? Sine 30 is a half. Okay. Well, can somebody tell me what this is? I can calculate it real quick. Times 240 plus. I got 413.21 kilometers.
That's what I got.
Thank you. 413.21 kilometers. That's X final. You're out here at 400 and you travel 413.21 kilometers in the X direction, and negative 100 kilometers in the Y direction. Okay? So now we can figure out delta R. That's easy because the position vector really is delta R. R initial is 0, 0. So delta R, what am I going to get rid of? Let me see if I can squeeze it in over here. So delta R is equal to R final minus R initial, and R initial is equal to 0. 0 is 0. I don't need I hat, K hat, J hat, whatever else, okay? R final is equal to, so what I'm saying is R final is just going to be delta R. R final is 413.21 kilometers I hat plus, which is, I could put a plus negative, but oh well, or minus 100 kilometers J hat. That's delta R in component form. I could ask you, well, give me delta R in polar form, how far this distance, sum of the squares, take the square root, and you would have to find this angle below. Well, I hope it's obvious that that angle would be below the horizontal. Okay? Let us find the average velocity. Oh, before we do that, what's the average speed? Well, you went 200 kilometers and 240 kilometers, so you have 240 kilometers plus 200 kilometers, and it took 5 hours, 5 hours, so that's equal to 440, so that's equal to 220 kilometers per hour. That's not right. 220. Jeez.
I got 88.
88. Thank you. Must be insane. Well, I know I'm insane, but okay. 88 kilometers per hour. Yeah. Yeah. That's the distance. That's the ground you covered. That's how long you were on the train. Okay. Let's find the average velocity. That's a different animal because for the average velocity, we need delta R. V average is equal to delta R divided by delta T, and that equals 413.21 kilometers I hat plus, oh, I keep putting a plus, this is minus 100 kilometers J hat, and you divide all of that by 5 hours. So this is equal to 413 divided by 5. That's about 80, what, 82 point something?
Yeah, I got 82.642.
Kilometers per hour, I hat minus 20 kilometers per hour J hat. That's the average velocity in component form. Let's put it in polar form. I'll try to, I guess I can go ahead and erase this. Okay. So V average, when I write this, that means magnitude. Yeah. So this would be 82.64 squared plus 20 squared, all underneath the radical, kilometers per hour. And can you please calculate this? That's about, I don't know, should be about 85, I don't know. $87. All I'm doing here is taking the sum of the squares and taking the square root. That's going to be the average, that's the magnitude of the average velocity. What you got?
I got 85.03.
Okay, 85.03 kilometers per hour. Okay, that's V average, magnitude. What's the direction? Well, this one's not difficult. You know you're in the fourth quadrant, so you're good. So I want theta, theta V, I guess I'll call it. This is equal to the inverse tangent of negative 20 divided by 82.64. And it's going to be, I don't know what that is, about negative 12 degrees or?
Yeah, negative 13.
Negative 13 degrees. Okay. So the final answer, if you were to have to put this on a test, V average is equal to 85.03 kilometers per hour at negative 13 degrees. Or you could write 85 point, was it 03? Yeah. Was it 0.03? Okay. Kilometers per hour. 13 degrees south of east. Okay. Do you see the difference in the average speed and the average velocity?
Yes.
Okay. Thank you.
I know nobody else really wants to talk, I guess.
I know. You gotta dismute or unmute and all that. So, okay. By the way, I just was thinking tonight at I think 9. You can look it up online. I think 9:43, the International Space Station's gonna come across the sky. It should be visible for about 6 minutes, something like that. I think it's coming out of the southeast, and exiting northwest or something like that. But it's a nice clear night. It's about 9, I think it's 9:43. So if you remember, go outside and you should be able to see it. I mean, if you've never seen it before, it really is pretty cool because it looks like a star, but the thing's moving like crazy. And you don't need binoculars or if you want to use binoculars, that's one thing, but you don't need binoculars. A couple of weeks ago, I happened to be up at like 4 a.m. for whatever reason. And I went outside and it was super, super bright. I mean, I saw it pass across the sky. It's only about a 2-minute interval, but if you've never seen the space station, it is a huge structure up at about, how many miles is it above the Earth? If I happen to know. Got this big space station up there going.
I have no idea. A huge space person.
A huge number?
Yeah, I'm sure it's massive. I'm not a
Okay.
space person.
Okay, you're not a space person. All right. Anybody else want to? I know, you can look it up before I can. It's about 200 miles high. About 200 miles. Yeah. Is that huge? No. The moon? That's huge. Mars? That's astronomically and possibly far away, I think. But I mean, for humans to travel, but we'll see. But yeah, the space station's only about 200 miles up, so it has to orbit really fast. So we will talk about that eventually. Geosynchronous satellites like the ones that you get DirecTV from, and not the spy satellites, but like the GPS satellites and so forth, they are pretty far away for geosynchronous orbits. So in other words, that satellite stays directly above the same point on the Earth. I think they're about 22,000 kilometers away, something like that. And of course, they have to orbit the equator. That's why if you ever see all the dishes for DirecTV and Dish and all that, they're always pointed south because those geosynchronous satellites are along the equator, way, way, way far away. So, okay, but yeah, tonight I highly recommend it. It's only 5 minutes of your time, so your valuable time. Let's talk for just a second about the acceleration of this train. Was there any? Go ahead.
I have a quick question.
Yeah.
Be visible, like, I'm in Georgia, so.
Georgia, you may have to check. It's probably visible, but it may only be for a couple of minutes. Let's see. How far south of Memphis are you? What city are you in?
Well, I'm like north,
You're in North Georgia.
like north-south towards Georgia.
North, south.
I mean, northwest, my bad.
Okay. North,
Like in north.
northwest. Okay, now I'm really confused. Okay. Check the internet. Check NASA's website.
All right.
All right. But in Memphis, if you're in the Big M, you should be able to see it. All right. Where was I? Oh, what about the acceleration of this train? Was there some acceleration happening? Yes, there was. Okay. The train was, let's look at this point where it made the turn. So I'm calling that little point where it made the turn. It came in at 80 kilometers per hour. It turned, we don't know how long it took for it to turn. I'll talk about that in a second. It turned and it went this way. This was 30 degrees. It went this way at 100 kilometers per hour. Okay? So it came in at 80 kilometers per hour and it made that turn to the south and sped up during that time. So if we can give some sort of number to how long this took, then we can calculate the acceleration of the train. Once it made the turn, it sped up. It continued along that path. No more acceleration. It was traveling at a constant velocity. So V initial was equal to 80 kilometers per hour. I hat. V final is equal to 100 kilometers per hour. And that's going to be, 100 kilometers per hour cosine 30 degrees. I hat minus 100 kilometers per hour sine 30 degrees, and I'll squeeze in a J hat down there. You follow me? That was the final velocity, was 100 cosine 30 minus 100 sine 30. Okay? So let's say that this turn that the train took 5 minutes. So it took it, that seems a little fast. Let's say, no, that's good. So let's say delta t was equal to 5 minutes. Okay. So for it to make that turn and speed up and all of that stuff took about 5 minutes. So to calculate the acceleration, this truly would be an average acceleration. We don't know all the ins and outs of what happened, but the acceleration, I'm just going to write it as the acceleration, is V final. And you have to subtract these as vectors. V initial divided by delta t. It's the difference in the vectors, not just the difference in the magnitudes. Okay? So let's write this out. V final, I'm going to get the numbers for this. V final is 100 cosine 30. What did we have before for that? Oh, we didn't have that, did we? So cosine 30 square root of 3 over 2. I think this should be 70 point something. What do you get for this? 100 cosine 30. 70.7? No, 86.6. That's right. Square root of 2 over 2, so okay. 86.6. 6 kilometers per hour. I hat minus 50 kilometers per hour. I can't write down here. Can't write anyway, but okay. J hat. So now we need V final minus V initial. So this is equal to 86, I'm gonna 86.6 minus 80 kilometers per hour, I hat, minus, okay, V final minus V initial. So V initial in the y direction, that's the x direction. V initial in the y direction is 0. So this is negative 50 kilometers per hour, J hat. And you divide all of that by delta T. Delta T was 5 minutes. I should have made it 6 minutes. That would have been easier. So let's put it in hours. So 5 minutes out of an hour, that's 0. What? It's 5 over 60. That's 1/12 of an hour.
It's like 0.083.
Yeah, I think that's right. Okay, 0.083333333333. Oh, okay, stop. Okay. 0.083 repeating hours. So the acceleration, if it took the train 5 minutes to make that turn, the acceleration is, that's 6.6 kilometers per hour minus 50 kilometers per hour, and you divide by 0.083 repeating hours. This should be a vector. This is I hat. This is J hat. Okay. So these are pretty big accelerations as far as the numbers go. That's because you're in kilometers per hour squared, which is a weird acceleration unit, but so be it. So 6.6, 0.83 divide. So I got 79.52. 79.52 kilometers per hour squared. I hat minus 602.4. I hope y'all are checking me on this, but that would be the acceleration in component form. Something's bothering me about this.
I got the same thing you did.
Something's bothering me about this. No, that's right. That's right. Okay. Well, let's see how to convert this to meters per second squared. So 79.52 kilometers per hour squared times 1 kilometer is 1,000 meters times 1 hour squared is 3,600 seconds quantity squared. You have to be careful. This is so easy to mess up. Okay. So let's see. We have 79.52 1,000 times 3,600. See, that's a really small acceleration. I got 0.00614. .00614 meters per second squared. That's in the x direction. That's in the I hat direction. This one will be bigger, but it's not going to be enormous. Let's see, 602.4. I got 0.0465 meters per second squared. Took it 5 minutes to make that gentle turn, so not a huge acceleration. And it is a vector, okay? Are there any questions on this? We're almost out of time according to our official clock, but any questions on this? All right, so tomorrow, well, I'll send out an email about tomorrow, but we should do projectile motion tomorrow, so that's what I'm planning on. Okay.